Hello, Mr. Claudia here. Today we are going to continue looking at integrals, but instead of looking at the indefinite integrals of the past few sections, that's where we have the plus c, we're going to start looking at definite integrals. Now there's kind of one caveat we're going to tell you right away, and we're going to sort of prove this later on. And I don't like doing it this way, but in order to kind of progress with today's lesson in a timely manner, I'm just going to give you this definition. So if you have some function, y equals f of x, the area under that curve, we can write that as an integral. So it actually turns out that the area under a curve is the integral of that curve. Now, if I want the area from a to b underneath this curve, that would be the integral of the curve from a to b. So here are the bounds. A is the lower bound, b is the upper bound. Again, I'm not really going to prove this. There is proof out there. We will get some more information about this, but this is sort of the central idea of what's coming, of what we're going to be doing over the next few days. And this is also the second central idea about calculus. The first idea, which was in Chapter 2, differential calculus, it revolves around the slope of the tangent line, or the slope of the curve. The second problem in calculus is the area under a curve. You've maybe seen this in a few areas before and knew that this was kind of coming. I'm a physics teacher. This comes up when we start looking at the area under a force displacement curve, which is work. We can do it if we have very easy curves that are squares or rectangles, but once we get curves, well, it becomes a problem, and we're going to need calculus to actually find the area under a curve. So this is a major thing. This is the other pillar of calculus, and that's and we're going to see over the next few days how we solve questions like this. So there's our introduction. So let's start by just understanding this notation. The integral. So this is a definite integral because it has an upper and lower bound. This is, I should label this. This is the lower bound. This is the upper bound. Okay, so this is a definite integral because, so I don't want you to think of it as an equation. This is an area. An area under the curve y equals 3. Well, y equals 3 that's an easy curve to draw. That's just a horizontal line. Y equals 3. And we want to know the area under the curve from x equals 1 to x equals 3. Well, x equals 1 is about here. X equals 3 is somewhere here. Right, there's my x equals 1, there's my x equals 3. So if I gave you that integral, well, you just need to find the area of this. So it's asking you to find the area under y equals 3 from 1 to 3. And that's pretty easy. That's just the area of a rectangle. The height of my rectangle is 3. The width of my rectangle is 2. So I can rewrite this. Oops, I'm just going to move this up. The integral of 3 dx from 1 to 3 is equal to the area under the curve between 1 and 3. Well, that's easy for one like this. It's just length times width, which is 2 times 3, which is 6. So the integral, this definite integral is 6. Now, if you don't believe me, again, I can take my calculator. This is something that when we get to the calculator, I'm going to show you how the calculator can do things like this. But here, we'll just do a quick version now. If I go to calculate, and I press menu, calculus, numerical integral, it can find this integral. So from 1 to 3 of 3 with respect to x. Yes, the answer is 6. So this isn't just made up, but this is kind of it's a geometrical way of solving it. You have to just make the graph. Let's look at the second one. So this is saying find the area under the curve 2x plus 1 from 2 to 6. Well, 2x plus 1 is a linear equation. It goes through the y-intercept of 1, and it has a slope of 2. So, I don't know, it looks something like this, I guess. We're just sketching it. And we want to find the area underneath from x equals 2, so somewhere here, to x equals 6, somewhere out there. Okay, so let's see if we can, okay, you want me to color it in? Okay, so this is 2, this is 6. Okay, so this is easy enough. The distance here is 4. But actually, this area is a bit more complicated, right? This area was a rectangle. This area is a little different. What I'm going to do is divide it. Sorry, this is the curve y equals 2x plus 1. What I'm going to do is divide this shape into 2 sections, right? So we'll call this A1, and we'll call this A2. Now, A1 is a triangle, A2 is a rectangle. We're going to need to know some other points to be able to figure out all the dimensions here. So let's figure out this point. At x equals 2, what's the y value? Well, 2 times 2 is 4 plus 1 is 5. So this is 2 comma 5. And this point 6, 12 plus 1, that's 6 comma 13. So now I can figure some things out. Like this height is 5 to 13, that is 8. And this then would have to be 5. Great. So now, again, this integral from 2 to 6 of 2x plus 1 dx is actually area 1 plus area 2. Now, area 1 is a triangle. The area formula for that is half base times height. And the area of the rectangle, A2, is L times W. So half 4 times the height of 8. And the area of A2 is 5 times 4. Isn't this fun? So now I have half of 4 is 2, so 16 plus 20. So my area, my definite integral is 36. Whew, okay. Look at this question. I still remember this question from my first year calculus final. Because we give you an equation like that. I can't actually find this algebraically very easily, but I can graph it like I did here. Now this shape, you might not recognize it. Let me show you. Y is equal to square root of 1 minus x squared. If I square both sides, I get 1 minus x squared. And if I rearrange this, I get x squared plus y squared is equal to 1. Hopefully you recognize this. My grade 10 students never do. But this is a radius. Oh no, it is not. It is a circle of radius 1. Hopefully you remember the equation of a circle. That's what that is there. So this is half of the circle. So this is y equals. Remember, circle is not a function. It doesn't pass a vertical line test. The positive root does, though. So this is a half of a circle. The other half would be y equals negative square root 1 minus x squared. But in this case here we have the circle, or half the circle. And we want to know the area between 0, x equals 0, and 1. So we want to know actually the area of half this circle. So again, I'm just going to write it out. 1 minus x squared dx. That integral is really the area of a circle. Then I take a quarter of it, so divided by 4. The area of this circle, the area is always pi r squared divided by 4. What is the radius? Well, we already said it was 1, so you end up with an answer of pi by 4. It's neat how you have to use geometry to find this integral, because yes, it's very difficult to do this algebraically. Let's do one more example. Okay, this is a line, so it's x-intercept of 1, and it has a negative slope. So, or slope of -1, so it looks something like this, I guess. Make that a little longer. Okay, so this is y is equal to negative x plus 1. Now, we want to know the area under the curve from 2 to 4. So 2 is somewhere here. 4 is somewhere, I don't know, over here. Didn't draw that long enough. Because this is 1, 2, 3, 4, I believe. Starts at 1. Anyways, you can verify my drawing, but I believe that's correct. So we want to know this area. So let's write that out over here. The integral of 2 to 4 negative x plus 1 dx. Well, this shape, again, I could break this up into a rectangle and a triangle. I'm actually going to show you one other formula you can use, which is the area of a trapezoid. I don't think this, actually it might be on your formula sheet, you guys can check. I can check if you really want. Hang on. Oh, okay, hang on. Sorry, I'm not upset. Area of a trapezoid. For some reason, this is in your formula sheet. So there you go, you have it. Anyways, the area of a trapezoid says that if you want to find the area, you take the base 1 and base 2, and you multiply it by the height. So I have this base and this base. Add them together and multiply by the height. You take the bases are the two parallel sides. So if you want me to rewrite this, this is h. So this is B1 and this is B2. Very good vitamin. Okay, so there's the upper area of the trapezoid. So I'm going to treat this like a trapezoid. So this height, if you want to look, this is a trapezoid on its side. The height is equal to 2. What is this point here? If I sub in x equals 2, I get negative x plus. So this is 2, negative 1. And this point here is for negative 3. So this base, we'll call this what? Base 2. This is negative 3. This base, base 1, is equal to negative 1. So to find the area of this triangle, I go half B1 plus B2 times h. That's my formula for area of a trapezoid. Sub in my numbers, negative 1 plus negative 3 times 2 is my height. I end up with half times negative 4 times 2. This gives me half of negative 2 times 2 is just negative 4. The reason I like to include this example, it shows you that negative area is possible. What does negative area mean? Well, in these questions, the area is positive because the area is above the x-axis. In this example, the area is below the x-axis, which means it's a negative area. So let's make a note of that. An area below the x-axis corresponds to a negative definite integral. That's an important distinction. I'd be as crazy about this distinction. So if someone asks you this, the answer is a negative answer, because when you draw it out, it actually is below the axis. Okay, let's turn the page. Now we have a graph that's given to us. We can interpret this to mean find the areas, right? Find the area from 0 to 8 between this function, g of x, and the axis. Now, here we sort of have different parts. We have this section, which I'm going to call A1. We have this section, which I'm going to call A2. And we have this section, which I'm going to call A3. So in other words, the integral from 0 to 8 of g of x, that's the definite integral, is equal to these three areas added together. Okay, now A1 is a triangle, base times height divided by 2 is the formula. Then the A2 you can divide into pieces, or you can use that formula for the trapezoid. And then a3 is another base times height. Now watch, this is kind of fun. We're just going to sub in values. So we have half, the base for the first triangle is 2, the height is 1. The second one is the trapezoid. This is the one that might confuse us. Well, we have the two bases. One of them is 1 wide. This one is 1, 2, 3 wide. So I end up with 1 plus 3 times the height, which is -1. So it's just -1.
Any caretaker, unlock portable 8, please. Could any caretaker unlock portable 8? Thank you.
The third area is half 1, 2. The base is 3 and the height is 2. Now look at this. You can already see what's going to happen here. This is a positive area. This is a positive area. Look at the second area. It's negative because the height is -1. So I'm going to get a negative number, which makes sense. When I do the math here, I end up with 1. This is 4. Divided by 2 is 2. So -2. This is going to be plus 3. So I end up with 4 minus 2, which is 2. So you can kind of see what happens here. This is positive, and then this kind of counteracts some of the area here. So I have actually this, and this is 1, this is 3. That would be 4, but then we take away the 2 negative, we end up with just an area of 2. So area, the definite integral so far is just finding areas, which is kind of fun. There are some properties of definite integrals. These are some of the useful ones, and we can see that we could prove these using areas, but we'll go through them one at a time. So first of all, if I wanted to find the area underneath f of x from a to c, well, I could actually find the area from a to b and then from b to c. And again, all of these are kind of rooted in the geometry of it. So if I were to graph this function like this, y is equal to f of x. Well, from A to C, so that would be all of the area from here to here. I could actually split this up into 2 areas. So this would be from, let's just finish my drawing. So this integral under the curve from A to C is the same as the area under the curve from A to B plus the area under the curve from from B to C. So that makes sense. You can imagine the logic of it, but there's one of the manipulations we're allowed to do. And all of them have similar setups. So if I have, okay, so this is an area under the curve with a constant in front, I can actually find the area and then multiply it by the constant. So I can pull the constant out. If I have, I'm adding 2 functions, I can actually find the areas independently and then add them together. If I have, this is a valuable one, if you have the area under a curve, it's a definite integral from a to b, you can, if you want to switch those 2 limits or the 2 bounds, then this becomes negative. You switch the sign. Finally, the area under a curve from a to a is just 0, right? The area from a to a is just 0. There's no area contained. The start and finish is the same point. Those are my 5 most useful properties. And we're going to get, you might see some questions like this where you have to do some clever manipulation of definite integrals using properties like this. For example, find the integral of 3f minus g from 0 to 2. So first of all, I'm going to use this idea, this third kind of property, where I kind of take well, this is the difference, and I split it up into 2 definite integrals. So I end up with, I'm sorry, we're a little tight on space here, 0 to 2 of 3 f at x dx minus 0 to 2 at g at x dx. Notice that you always have to have dx, right? Dx and the integral sign, they go together. And we use the same limits because that's what we did here. Right here, same limits. Now, I can use my second property and I can bring the constant out. I mean, that's very similar to what you see with indefinite integrals, which we've done in the past few days. Now, look, they've defined these things in the question. So the integral of f at x from 0 to 2, that's just 4. So this is actually going to become 3 times 4. And g, the integral from 0 to 2, is negative 3, so this becomes minus 3. So that becomes 12 plus 3, which is 15. So in this way, they're testing your understanding of definite integrals by giving you some of the values and getting you to do some manipulation. This second question, we have the integral from 2 to 2. Well, the area of that would be 0. And we have the integral from 5 to 2. Well, that's backwards, right? And we don't know from 5 to 2. We know from 2 to 5. So what I told you is you can switch the limits in the opposite order if you switch the bounds if you put a negative in front. So there we go. I changed the sign. Then I can do my substitution. So the integral of f of x from 2 to 5 is 12. So my answer ends up being negative 12. Okay, the integral of f from 0 to 5. We weren't given that information in the question, but we were given the integral of f from 0 to 2 and then 2 to 5. So I'm going to rewrite this using that first rule that I showed you up here. We go from 0 to 2, f of x dx, plus 2 to the 5, f of x dx. Now I've been given these values. This is 4 and this is 12. So I end up with 16. Next one, okay. We want to find out the integral of g, or the area underneath g, from 2 to 4. Now I've been given from 0 to 2 and 0 to 4. So you have to imagine that I'm sort of, if I could only subtract this area from this, I would be able to figure out this area. In other words, think of it this way. The area from underneath g of x from 0 to 4 is equal to the area from 0 to underneath g of x from 0 to 2 plus from 2 to 4. Now, if I want to figure out what the area under the curve from 2 to 4 is, I could rearrange this. As the area from 0 to 4 subtract 0 to 2. I just rearranged. I wanted to get this by itself because that's what I'm trying to find in this question. So as you kind of imagine, I took the area from 0 to 4, which is 6, and I subtracted the area from 0 to 2, which is negative 3, so I end up with 9. Oops. It's a confusing one. Actually, no, this is the worst one here. I want to find out the area under the curve f at x plus 3, and look at these bounds. I don't have these bounds at all in this question. So what's going on here? Well, first of all, let's bring the half out, because that is something I can ignore. That's just distracting me. Okay, what does it mean f at x plus 3? Well, this is why we taught you so much about functions. You guys have done a lot of transformations, and this is a transformation. A transformation has been applied to f at x. What is the transformation? Well, it's inside the bracket, it's positive, so you'd think it would go to the right, but it's actually reversed. It's a horizontal shift to the left. Horizontal shift of 3 to the left. So this is, you can understand what happened here. This function was, we want to find the function that's been shifted to the left. To do this, we got to shift it back to normal, because look, I've been given the information for f at x, not at f at x plus 3. So if I want to go back to normal, remember I've shifted 3 to the left, how do I do that? Well, I have to shift everything to the right by 3. So this negative 3, imagine where that is on the number line, I want to shift that to the right by 3, so it's going to go to 0. This negative 1, I'm going to shift it to the right by 3, it's going to go to 2. And this f at x plus 3, it's going to just become f of x because I've undone this. I've shifted it to the right. This is a little counterintuitive. This is why I put these big notes here. To go back to normal, we must shift all x's to the right by 3. So you're undoing this shift to the left by shifting everything to the right. So you succeed in making this f of x, and these all move plus 3 to the right. So look, now we have an easy question. The integral of f of x from 0 to 2 is right there. It's 4. So this is half times 4, which is equal to 2. That's the hardest type of question you can see for that. So our homework for tonight is just looking at this definite integrals. Actually, we don't do any integration, really. Today's homework is all about understanding that these are areas. Oh, sorry. So there's your homework. Good luck, and we'll see you next time.